what I spent some time on. The square root of j is 1 plus j over square root of 2, right? So I can say that's really 1 plus j over square root of 2 times the square root of omega mu sigma. Now you can leave it like that, but one thing you can see just by looking at this, you can see the coefficient of 1 is the same thing as the coefficient of j, and therefore alpha is beta for a good conductor. I hope that answers it in a way that reveals everything about it. And whenever you look for propagation constant, you always go back, for alpha and beta, go back to gamma. That's what I tell everybody. Don't mess around just looking for a shortcut, because this will always work. To be honest with you, you know, you guys have good calculators. That is not hard to do on your calculator. I'll make one more comment. Usually when I do problems, if I have to use a calculator, I have something where I enter either F or omega, typically F, then mu, sigma, and epsilon. Epsilon relative and mu relative. I have mu naught and epsilon naught stored. So most of your modern calculators have those things embedded. They have C too, I think, the velocity of light. I'm not absolutely certain, but a lot of them do. Anyway, if you have those available, or if you're writing a program, when I enter it, like in a script file, I simply put in F, sigma, epsilon relative, and mu relative. I got all those at the front of the script. Now, right away, I just bang off, I get omega, I get gamma, which is alpha plus j beta, I get the intrinsic impedance, right away I get the phase velocity, get the wavelength, boom, got all the quantities. Now what do you want to know? And it sort of goes from there. So those will always be the same, no matter what. And that's the way I do it. So, that's about time. It's time. So let me ask you this, are you recording this too?
Yes.
Can you load this up to YouTube and Zoom or not? Or can you only get to YouTube?
I can only get it to YouTube.
All right, I hope everybody that's not here won't mind. I'm sure they'll.
For what?
I suppose give me 1 second. I'll try to get them on Zoom class here. How's that? I mean, I think I can. Oh, no, I can't. No, use your camera. Never mind. They'll figure it out. As long as they got that lecture, that's all that matters. How many we got here? 2, 4, 6, 8, 10, 12. We're missing, say, 8 students. Now I want to ask everybody this. Have you looked at the lectures that he posted, or the other lectures? How many have? If you have, did you have any problems with them, anything? All right, I prefer YouTube myself, and this is the one simple reason. Zoom sometimes is not, or Panopto actually for here, I have to use Panopto. It will not, at times, it has problems with keeping that information available to you or recording it. And didn't this class have some problems seeing some of those lectures before? It was my other class. All right. Anyway, I wanted to tell you that. So anyway, that was a little backtracking. Now, today, let me throw this out there. And for those of you who came recently, did anybody have any questions about any of the material covered up to this point? Any homework problems? Any questions? Any concerns? All right. Now I'm going to talk about polarization. Let me start by saying the way it's done in the book is not something I can really test you on, but you should be aware of it. And a simple question, if it's right-hand or left-hand circuit polarized, is in order. So that sort of starts the lecture. Gives you an idea what I'm looking for. Now, when you talk about polarization, this is section, if you're looking in your book, it's 6.6. This is section 6.6 in your book. When you're talking about polarization, what you're really doing is assuming you have a propagating electromagnetic wave in the far field, but now it may not have just an X or Y component. Y'all follow me this? So let's start by taking a look at a wave coming right at us. Call this the X-axis, call this the Y-axis for now. And we're going to assume the wave's coming right out of the board. You have to get a mental image of this. I can't draw this in 3D as well as I'd like, so I'm trying to just give you a 2D projection. So we've got an electromagnetic wave propagating out. And if you freeze time, you'll know you get something like this as far as the envelope. Can everybody imagine it? This is a propagating electromagnetic image. But in the plane of the board, if you take a snapshot in time, if it is an X polarized way, then the electric field will have a value that grows this way in time, right? And as we let time progress, then it'll shrink and go this way in the plane of the board. Now, admittedly, it's propagating this way, but if we only look at the projection into the board, can you all visualize this? It'll just be up and back. And it will follow cosinusoidal variation or sinusoidal variation. That is called, that when the electric field only is polarized in one direction, it's called linear polarization. I'm going to get this down. So if it's polarized in one direction, it'd be linear polarization. I just want to tell you what the different polarizations are, and you'll see it. Now, the next type of polarization is this. We have an electromagnetic wave in the X direction, polarized in the X direction, propagating out of the board. We also have one in the Y direction. Does this make sense to everybody? So when we look at the total electromagnetic field, it could be something where the electromagnetic field just grows along a certain line and then grows along the opposite line. It looks like linear polarization, only it's got a tilt angle. Does this make sense to everybody? And I'll give you the equations in a second. I need to give you the picture first. That's one possibility. Another possibility is that the electromagnetic fields in the X and Y could have the same frequency. They do have to have the same frequency for this to work. But they could be out of phase. And if that's the case, when the electric field in the X direction was at its peak, like here, the electric field in the Y direction could be a minimum. Y'all follow me? And by the same token, when the electric field in the Y direction was a peak, the electric field in the X direction could be a minimum if the phase shift was 90 degrees and the amplitude was the same. And you would have something like this. And actually what you would have is the peak of the wave. If this is the electric field vector in a snapshot of time, it would be doing this. It would be rotating. Now, can you imagine that in your minds? In the plane of the board, sure. That is called circular polarization. The thing you'll notice is the peak value of the electric field never changes, only the orientation. Admittedly, it is propagating out of the board, and I'll give you the equations in a second, but you need to see that. Does everybody see that? The equations at this point aren't that useful. Now, the way we dictate, you're smart, you realize this. Well, the electric field in the plane of the board, if it's propagating out, could be going this way, or it could be going this way, right? In terms of its increase in time, how it would vary. Do y'all follow me in that? I'll put this down in a second. When a wave has what's called right-hand circular polarization, you take your right hand. That's one of these things. I have yet to have a person without a right hand, but I'm sure at some point in my career, that's going to happen. Anyway, if you have a right hand, take it. Put your thumb in the direction the electric field is propagating. Can you all see? I'm trying to show it on the board. Now, if you take the fingers on your right hand and it goes counterclockwise, if I have X, Y, counterclockwise, that's called right-hand circular polarization. It's not that important, you know it right now. Conversely, if you take your left hand, put it in the direction of propagation, and the electric field goes this way as time's increased, it's left-hand circular polarization. The key is your thumb points in the direction of propagation. Don't think too deeply, well, what am I going to ask about this? I'm not going to ask if it's right or left-hand circular polarized. Dr. Whitworth might. So that's not important. Here's what's important to know about that. And I do radar work. When you have radar, if you put out a right circularly polarized wave, so it's going like this, and it strikes a target, this is a conducting target, it would generate a left-hand circular polarized wave coming back at you. You all follow me? Now that makes discrimination of what I sent very easy. If I know they're trying to jam me, for instance, all right? If I send out a right-hand circular polarized wave, they don't really know, well, they could if they're clever, what kind of polarization. But I can discriminate the actual target reflections from other incoming information at that same frequency. Do y'all follow me? Because I can put what's called this polarization filter. There's right-hand and left-hand polarization filters, and I could say only right-hand or left-hand polarization at that frequency would I accept and look at. Everything else I discriminate and get rid of. That's the reason polarization is so important. You all follow me? Now you can't do that with sonar. There's some, I'm going to try to always contrast this. If you're dealing with a sonar system, the actual waves in air and water, not in the earth, but in air and water, are either compression, where the atmosphere compresses, or refraction, where it expands, and that's how it propagates. Do you all follow me? When you're dealing with electromagnetic energy, the electric field, you could think of almost a force vector, is perpendicular to the direction of propagation. It's not along the direction of propagation, and that's why it can discriminate so much better than sonar in identifying types of target and location of targets. Now there's more to this, but you all following this? The velocity of light's much higher than the velocity of sound, even in water or dense media. But this is something to keep in mind. The big difference is being able for the electric field to have a polarization when you launch the wave and then use that polarization for discrimination purposes. Something else I'm going to say, and this is more for weather radar. It doesn't have to be a circle. I'll give you the math on this one in a second. The math isn't that important as you see what's going on. If this is X and this is Y, if you look at the tip of the electric field vector, it could be straight, that would be linear, right? It only has one projection, there's no oval. But another one would be that the electric field itself would trace out something that is not a circle but an ellipse. They should make sense to you, right? That's when we would have an electric field in the Y direction would be of different magnitude than the peak electric field in the X direction. Follow me? Then you would trace out an ellipse and what's called the actual tilt angle or of the ellipse. And Whitmer's book, I think, does it this way. He calls it this tilt angle. That's not that important. The tilt angle there would have to do with the phasing of the two. We'll talk about that in a second. But you could get basically, with very little effort, I can generate either right or left-hand polarization, the mathematics, and I can get either elliptical, linear, or circular very easily. Do you follow me? Mathematical. The key is that you see this. Where elliptical polarization becomes valuable is in weather radars, and here's why. When you send out a wave, if your target is very long and thin. Just listen to me now, and it's a conductor. I'll try to, I don't have a yardstick here, but if you can imagine something like this. You have this, and you send out an electric field, assume it's a conductor. Right? Send out an electric field that's vertically polarized and it hits it, it'll get the maximum reflection if the electric field is aligned along the maximum or the lengthy axis of the target. You with me? Now, if you have an electric field polarized this way, and it sends out, hits its target, you'll get a minimum. With me on this, everyone? That's real important. Now, that tells you if you see a target that looks like an ellipse, what you would like is the target to have an electric field that would, a polarization that would mimic the outline of that ellipse if it was a flat plate. Make sense to everybody? When you launch it, in order to get the maximum return for the given amount of power. So why is that useful with rain? There's more to this. Rain, when it falls, and grapple is like slush, or hail, all have distinctive size patterns. Rain has what's called a teardrop, a fairly long axis and fairly narrow horizontal axis. So when they do Doppler radars and stuff, they send out polarization signals where the return, if it's rain, they can detect by the polarization of the sense signal. If it's hail, they get a different return. And if it's, I call it slush, it's called grapple, they'll get a different return as well. And they can distinguish what's out there pretty much by the return. You with me on this? So that's where elliptical would really be beneficial. There's other reasons for this too. I'm not a real fan, I don't know a lot about atmospheric pollution and different types of pollutants, but I know different types of things that are man-made as well as naturally occurring like volcanic ash have a different type of return, and they can to some degree distinguish it by the polarization that they use. Okay? And just keep that in mind in the back of your head, because it's information you should at least be exposed to. So mathematically, how do I do this? Well, Dr. Wentworth has some mathematics. Let me just tell you this. The way you normally do it, you're going to say, forget propagation in the z direction. I'll assume I'm at z equals 0, and the wave is propagating in the plus z direction. And what they'll do is this. They'll say, my electric field, total electric field, will be some E naught x times cosine of omega t. Now there's no beta z here because it's not propagating. It's already just at the z equals 0, right? So there's no beta z term here. Follow me? And it's going to be plus some phase angle. Then it's going to be plus E naught y times cosine of omega t plus phi y. And let me do this too. I should put an ax vector here and an ay vector here. You'll understand this, I think. So that's electric field. I made z equals 0. Now I could put in, all right, minus beta z here and minus beta z here. But it serves no benefit for exposing what I'm trying to do. Do y'all follow me? What I'm trying to do is expose you how to get the different rotations in different magnitude. So now, if you want linear polarization, linear is straight line, right? For linear polarization, what you want is the phasing of this wave and this wave to be the same. So you make phi y and phi x the same. That's an easy way. There's more ways. Do you all see this? Now think about what happens if you make phi x and phi y the same. Here you make phi x equal to phi y. And for our purposes, let's make them equal to 0. By the way, in the far back, can you see it, sir?
Yes, sir.
And I'm going to ask you this much. As much as you can space out, looks like a lot of people probably doing this online, and thankfully you're recording, and hopefully it'll work, and we'll be able to put it online for everybody, and that's fine with me. I kind of wish it was interactive. I'll mess with this later. And I'm actually looking for another room too, where this board will be done away with. I actually have a whiteboard to work with, all right? But let me know if there's anything I can do to help you better understand what I'm talking about. I'm not trying to talk fast, and I don't have a face shield. I don't know, remind me. I'm on my second face shield.
It's on the other side of that table right there. Unlike the in between the wall and the table.
That's probably mine. That would be mine. Thank you. I'm glad you have eyes to see. I guess when you get old, you miss things like that. All right, guys. Let's see how, I feel like I'm wearing a welder's mask. Can you hear me okay with this? If for whatever reason you can't, honestly, just yell. And can you hear me with that mic?
Yeah.
I need to talk loud. All right, look, when you have this, take a look at those equations and what happened. I'm going to do linear and I'll do elliptical, or we can do circular too. But if you look at this, what happens? I get an E field here equal to simply E naught x, right, times cosine of omega t, ax, plus E naught y, right, times cosine of omega t right here. Now just take a look at that for a minute and plot some points in your head. Here's x and y. Remember, we're at z equals 0, right? This is ay. No, actually, I like the mask better. I'm being honest with you. I'm not a real fan of any of this, but we gotta do what we gotta do. I like it. Can y'all hear me up there with this? All right. If you can't, let me. If you look at this, just plot points. Start at omega t equals 0. All right, where's that point? At omega t equals 0, both x and y right there. I mean, cosine of 0 is 1, right? I got 1 and 1 there. So I got E naught x, E naught y. Somewhere in the x-axis, this would be E naught x. Here, it would be E naught y. You all see this? And that's going to be a point right here. So your vector's up there. You agree with me, everyone? I'm just trying to show you, this is the point where this would be E naught x, this would be E naught y at t equals 0. Now what happens when omega t is equal to pi over 4? Well there, that's like 45 degrees, right? Pi over 4 is 45 degrees. The cosine of 45 is 1 over square root of 2, right? 1 over square root of 2, both places, times E naught x, times E naught y. If you look, you're on the same line. You would be here. You all see that? And then you can go through this. You all see how what actually happens is you're going to get nothing but a straight line if you take a look at how that tip traces out when it's circular polarization. I'm sorry, linear polarization. You all agree? I got a question for you. How would you make that tilt angle 45 degrees? Yeah, but did you have a question?
I was going to answer that. Would you make E naught y and E naught x equal to each other?
If you wanted a tilt angle here 45 degrees, absolutely. You make these two equal, you see that? It would be 45 degrees. How many see that? Right, if you make the magnitude of this is equal to that, then the tilt angle is 45. Correct, class? What if you wanted it minus 45? Make what? You would make which one negative? Think about it just for a second. Well, I want to be negative this way, right? If I want it this way, let me ask you this. Well, what would I do? I'd want at omega t equals 0 to have positive EY, negative EX, so I'd put a negative sign there. Can you see this, class? And you can fuss with this all you want to get whatever you want. Now, here's the thing, too. Say I don't want that. I want a different tilt angle, right? I can change the magnitudes, get a different tilt angle, right? And if I want the thing to rotate a little more, I can do a lot of things, by the way. This is the crazy thing about this. There's so many ways to achieve the same result. What if I had a phase angle? Go with me on this one. I'm going to erase this and just say for now, this would be linear. Now, if I wanted elliptical, what would I do? And there's a lot of things you could do. Elliptical polarization. Well, think about it. Let me put it right here. What would you do for elliptical? Let's go with this one. And I'll tell you what, for kicks, just let's make these things the same amplitude. Make them 1. That way, we can mess with something else besides the amplitude. But what would you do if you wanted an ellipse? That's linear, right? Better yet, what if you wanted a circle? What would you do? Can anybody guess? I bet you most of you know you don't want to say. Yeah, go ahead.
Would you make the phase angles 90 degrees out of
You can either add or subtract 90 or pi over 2 on any of this. So if we make this omega t, either plus or minus, I'm going to leave it as plus pi over 2, what happens? And the way you find out what kind of polarization, you simply plot a few points at different values of omega t. Follow me, class? That's the easy way. And I'll always tell you what I would require you to know for a quiz. Now, if you look at this, we'll go to omega t equals 0, and I hope I can plot it down here. This is x, and this is y. When omega t equals 0, this is 1ax, right? So I'm doing omega t equals 0, 1, so this is really going to be 1 here. But what happens to this? Omega t equals 0, I have cosine of pi over 2, which is
1.
0, right? Cosine of 90 is 0. Do you agree, class? So it'd be 0. In other words, this would be where the vector is at omega t equals 0, right? Now stay with me. What if omega t here is equal to pi over 4, 45 degrees? Go back here, what happens? I got cosine of 45, which is 1 over square root of 2, right? About 0.707, right? Over here, what happens here? Well, what would I have? How about if I do it this way? I'll make this minus, you can see. I have what? Omega t is, I would make it pi over 4. So I have pi over 4, I'll make it plus. I'm trying to do this to make it easy. So I have 90 plus 45 is 135. What's the cosine of 135? Negative, isn't it? So it's doing this. And it would be negative 1 over square root of 2, correct? So the point here would be here, and here, it would be out here. And what you're seeing, without going through the whole plot, it's doing this, right? That would be left-hand polarization. Do you all follow me in that class? Now again, I'm not going to ask you to go ahead and tell me if it's right or left based on equations. I'm leveling with you, I don't do that. I just ask you if it is circular, linear, or elliptical. And you can get that very easily by just plotting a few points. Do you follow me, class? So now, that would be elliptical polarization, but it would be left-hand because the axes will be different. Or actually, sorry, it would be circular polarization. No, it would be elliptical. I'm sorry, it would be elliptical. And the way you'd actually do this, if you were really concerned about it, would be plot this thing using MATLAB or using Octave or using, I guess some of you use MathCAD, Mathematica, Python. I don't know what program students use anymore. I know Octave and Python are popular in the upper level courses. Are you guys in Python now, or do you use Octave and MATLAB still? Just MATLAB? That's fine. It's fine. Okay, anyway, I'll give you a few problems to do, but that's the gist of it. Now, if you want to get, we could go into elliptical right hand, elliptical left hand, all the things, just plot a few points for EX and EY and plot the position and see how the head of that vector is moving, okay? That's how you find this thing out. I don't ask you bizarre questions like, is with some bizarre formula, like, you don't have to use a cosine. You could use a sine. You don't have to use a cosine or a sine. You can add a summation of the two. You can have all sorts of bizarre things. But ultimately what you're doing is looking at the tip of a projection of a vector in a plane and how it rotates. That's the only thing, yeah.
If they're 90 degrees apart, the phase.
If they're the same magnitude, 90 degrees apart, it's circular.
Okay, it's different magnitude make it elliptical.
Yeah, and again, it has a certain tilt angle. Now, there's so many ways to get this, and it really is not that important, because in the real world, what you're dealing with when you got an antenna, there's two things you worry about in the real world, and this is for radar and most applications. They don't use theta and phi as the azimuth. What they'll do is have elevation. So they're going to have something, and you're going to have how high you are from a vector that's parallel with the ground. It's called elevation. It's really the bore site, but elevation, and then they have azimuth. And that is how far on the projection on the horizontal plane you are in one way or the other. So you could be 30 degrees plus azimuth, means this way, 30 degrees negative azimuth this way, and you always come out, and I'm talking from experience now from the radar world. In our book, you have theta and phi, right? It's the two angles for circular. In the real world, with radar work, aircraft work, my wife's doing work at Archangel. It's an embedded systems thing. She's a trained electrical and computer engineer, a master's. All the stuff that they're going to do is azimuth and elevation. All right? It's not theta and phi. That's for us guys in electromagnetics, where we do antenna design theoretical. And you know what I'm talking about when I talk about that. Azimuth is theta, we just call it theta, is always from a vertical axis, how big the conic angle is, the opening, right? And when we talk about phi, it's always measured in the XY plane, and it's how the hand, the projection of your radius vector, how the hand is, the shadow where it lies, if you're moving from the x-axis in the positive x direction, that would be phi. And I think you know this, but it's much different than the real world when you do azimuth and elevation or elevation and azimuth. Okay? Now, I'll give you a few problems on this. I think most of you will probably do very well with problems, but I need to expose you to it. You can read through Wentworth stuff. He puts it into phasors. There's no need to put it into phasors. The only thing you do is look in the XY plane. I'm telling you that. At z equals 0 on the XY plane. Now, he talks about reflection and transmission next. This is important, and I'm going to take you through it in a way that should make sense, and I'm glad I have the board to do it. I can give you a PowerPoint about this, and but honestly, I don't think you'll have any problems, any difficulty with the problems. Now, this is section 6.7, it's reflection, but it's from normal incidence. And put down normal incidence. So what do I mean by normal incidence? In a nutshell, it means if you have an electromagnetic wave propagating, it runs smack dab into a wall, normal or at 90 degrees. The propagation vector is 90 degrees into the wall. Following? That's normal incidence. Oblique incidence is when the wave is coming like this. This would be propagating, and it hits, reflects off. Think of a pool table. Normal incidence would be hitting a ball from the spot right directly into the bumper. It reflects back over the spot. That's a normally incident wave. Oblique incidence is when you shoot into a bumper and it reflects off at the same angle. So now we're talking about normal incidence. This is the most common way. And we're, again, this whole chapter we're talking about plane waves. It's page 553, or sorry, 353, if you look. Are you looking for it, sir? 353.
Yeah.
Section 6.7. All right, so here's how I do this. I go ahead and I write the equation in phasor space, in phasor domain, and then I match boundary conditions. So let me do this. We're going to assume we have region 1, and then region 2. All right, so this is region 2. Now I have an electromagnetic wave in region 1. I'm going to give this some coordinates so it can make sense. Let's call this the z direction. And let's be consistent, call this the x direction. So a wave's going to be assumed propagating in the z, but oriented in the x for the electric field. So here's what happens. I have an electromagnetic field, Ex, or just E here. And you can do this, the way Wentworth does it is, he puts a superscript right here. Can you see this in the back there? Yes. This is going to be an electric field, and it's going to be some E incident pair. And call that E naught incident, E to the minus, let's do this stuff for lossless case. If we do it for, we can add something in a second to take care of the lossy case. It would be E to the minus J beta 1 Z in the AX direction. I hope you can appreciate that wave is going this way. And it strikes it, right? Now, some of this wave's transmitted. So here you're going to get electric field. And that would be E transmitted equal to some E naught transmitted E to the minus J, but here it's going to be beta 2, and beta 2 times Z in the AX direction. All right, so the wave comes, hits, some of it's transmitted. This should make sense to everybody, right? We don't know how much it's transmitted, and some of it's reflected. So when we have a reflected wave, we're going to have an electric field reflected, and that's equal to E naught reflected E to the plus J beta 1 Z A X. The reason it's plus J beta 1, it's going in the negative direction. Okay? I'm just showing you this here. I'm going to break these out when I start doing math on them, all right? You got an electric wave going in, electric field in X direction, striking this surface between region 1 and region 2. Some of it's transmitted, some of it's reflected. Now, each of these two regions has different, possibly different eta 1, and it'll have some impedance here in this region. I'll call it eta 1, that's intrinsic impedance. This region will have an intrinsic impedance eta 2. This region will have some beta 1, if it's lossless, equal to the square root of really omega times square root of mu epsilon. mu1 epsilon 1. And this will have some beta 2 equal to omega square root mu2 epsilon 2. Now remember, these etas, I can put it in here, but eta is really equal to the square root of j omega mu. In general, it's got sigma plus j omega epsilon. And eta 2, in general, we're making, assuming sigma 0, the square root of j omega mu, and this would be sigma 1 epsilon 1 mu 1 mu 2 sigma 2 plus j omega epsilon 2. Only thing I'm doing here is trying to give you some context to what things are really controlling these values. It's basically the intrinsic parameters of the region and the frequency. Everybody with me? Now, if I look at this, those are the electric fields. So I'm going to put them up here. And we know one thing that everybody here knows from EMAG 1, or you should. You know that whenever you have a boundary between two regions, there's two laws that are overwhelmingly true if there's no currents that are force currents at that region's interface, the surface between them. One is that the tangent electric field on one side is equal to the tangent electric field on the other side. How many remember that? It's E tan 1 is E tan 2, right? How many do, really? Okay, if you do, good. You have to know that. The electric field on one side, the tangent field. When I say tangent, I'm going to do this show here because some people don't understand. If this is the electric vector, if the propagation is this way, and this is the E field, this electric field is tangent to the wall. The entirety of it is projected onto the wall if you took a shadow from a light source here. Non-tangent would be something propagating like this. Here, a portion of the electric field is tangent, but not all of it. In non-tangent would be something where the electric field is propagating this way. There's no component of the electric field that shadows onto the board if there's a light source there. Does that make sense? Can you understand it? Okay, this is real important. Now, E tan 1 equals E tan 2, this means the total electric field in region 1 at the interface has to be equal to the total electric field in region 2 at this parallel interface. Do you all remember that when you did boundary value problems? E tan 1 is E tan 2. What's the other law when we talk about things without currents on the surface? H tan 1 was H tan 2. Do you all remember that? The tangent magnetic field on one side equal the tangent magnetic field on the other. And those are the two laws you use to solve this. So if we do one thing, if this is a z-axis, let's make this boundary right here z equals 0. So we're going to put the interface between the surfaces at z equals 0. Now, follow me. The electric field for z less than, or the electric field at the interface, it would be z equals 0. On region 1 would be E what? It would be E naught incident, right? And then it would be E, I'm just going to mention this. You see how if I'm right at the interface and I'm matching the field components, saying the electric field tangent on one side is the tangent electric field on the other, that z is 0, so these e to the j businesses go to 0. Does everybody see that? So you would have E naught incident plus E naught reflected would be equal to E naught transmitted. That's the first one. Does that make sense? It's at z equals 0. In region 1, you have an incident and a reflected field, so you have to evaluate both of those at z equals 0. In region 2, you have only a transmitted field. Correct, class? And you equate that to the transmitted field. It is in the x direction. Adding ax does nothing for understanding here, so I don't even put it in. Can you all see it and understand what I put down there?
Can you reread that equation?
Can I what?
Can you just reread that equation real quick?
This one?
Yes, sir.
The incident field strength right here plus the reflected field strength is equal to the tangent field strength. I'll write it larger to help you. It's the magnitude only. So it's E naught incident plus E naught reflected is equal to E naught transmitted. Okay? Now, the second thing was there's a reflected magnetic field and an incident magnetic field at the boundary that have to be the transmitting magnetic field. Let me tell you this right now. I'll put these equations right here. So when I take a look at the incident magnetic field, H incident would be really E naught incident over eta 1. That would be the magnitude. Do you all agree with that? If it's propagation? Yeah.
On the E field that's reflected, it's going to have negative magnitude, correct?
We don't know what the magnitude is.
Okay.
That's why these are arbitrary values. The only way we get them is by matching the boundary values. It's really the intrinsic parameters that dictate the polarity. Okay? Or the relative polarity. All right, isn't this right? E over H, right, would be eta, or really eta is E naught over eta 1, right? It would be this, then it would be still in phase. I made sure I let sigma equal 0 for this one. So they'll be in phase. Then it would be E to the minus j beta z a y, right? The incident H field would be perpendicular to the incident E field, right? Have the same phase, and would be simply magnitude would be E naught incident over eta 1. You all with me? Now the reflected magnetic field would be E naught reflected over eta 1, still eta 1, e to the plus j beta 1 over, beta 1 z. But there's one thing that happens here. I think I told you that the ratio of E to H when it's a negative going wave is actually minus eta, right? Do you remember that? How many do when I said that eta, the ratio of E for a positive propagating wave over H positive was equal to eta, right? But if you have the ratio of a negative going wave, right, it's minus eta. And again, eta, he calls it intrinsic, but it doesn't matter if you put a sub I here, is equal to the square root of j omega mu, right, over sigma plus j omega epsilon. Here we're assuming sigma 0, but there'd be a phase angle I have to worry about. Agreed, class? All right, that's the incident. The reflected field would have a negative sign here because of this phenomenon. We can prove this later if you really want me to. I can show you why that negative sign appears. There's a negative sign there, and it's in the AY direction. And then also, you have one other thing. You have H transmitted would be equal to H, it would be E naught, E naught transmitted over eta 2, e to the minus j beta 2, this is supposed to be beta 2 times z, and it would be in the AY direction. So, another reason this is a minus, I'll just tell you this. Take a breath. Remember how whenever you have E crossed H, it's the direction of propagation. Do y'all remember that? So if this is the x-axis that way, and you're going in the negative z direction, well, E crossed H, it means the H field would have to have a negative AY sense. Do you all see that? It would be E vertical, right, crossed into H would be that way negative. You good with that, everyone? So that would be the case. If it's not my car insurance, it's somebody selling me real estate, or do you ever have that your insurance is lapsed, and no matter how many numbers you block, they still find out, not lapsed, but your warranty is lapsed, they keep coming at you? Well, if you haven't, give it time, guys, you will. All right, so these are the three H field equations. And if you have an E field that's vertical, and it's propagating that way, the H field has to be perpendicular to both vectors, and it's also tangent, right? So H tan 1 is H tan 2, and over here, we're doing this at z equals 0. What that means is E naught incident over eta 1 minus E naught reflected over eta 1 is equal to E naught transmitted over 82. These are the two gold standards when you talk about normally incident waves. And in your book, these are shown. I'm trying to find out where they're shown. I think he does one of them in 6.108 and the other one 6.107 on page 355 if you have your book. Can you see it there, guys? So that's what I've come up with. That's the reasons for it. You should always know the reason. The difference between you guys and technicians is they don't know why a formula works. They got all these formulas. Here, you know the fundamental reason. Maxwell's equations admittedly came from measurements, but everything else is derived. And this comes from a fundamental understanding. So we've got these two equations, and what we really want to do is find something where both E transmitted and really want a function of like E transmitted to E incident or E reflected to E incident, the electric, in terms of the intrinsic parameters. And here's how we do it usually. You come down here, and you don't have to write this down, just watch, it's not hard. You can do it at your leisure. You see how I have E transmitted in terms of the reflected and incident. So if I go ahead and I replace E transmitted here with these two terms, then I have one equation in terms of reflected and incident electric field stream. You all see that? This is critical. So if I do that, you don't need to do it, just watch. Your book has it. Now I'm going to go ahead and put it E naught incident plus E naught reflected. Okay? I've just substituted. You agree with that? Some of you want to write it down, you go ahead. Now, what I'm really interested in is the ratio of the reflected to the incident electric field. Got it? The ratio of the reflected to the incident electric field. And I'm even going to give it a name, and I'm going to put it over here. That's called the reflection coefficient. So the reflection coefficient looks like this. The term is called gamma. And the reflection coefficient is the ratio of E naught reflected over E naught incident. So it's a magnitude ratio. Now we're going to get it with this equation. Just bear with me. Honestly, it's easier to just look and then you'll see the trick. So I'm going to divide both sides of this equation by E naught incident. All right? And when I do this, I get a 1 here, right? I get a 1 here. And then you see something. Well, now I have E naught reflected over E naught incident here, right? And that is the reflection coefficient. So I now replace this by gamma. And I replace this by gamma. You all follow what I'm doing here? I'm trying to just use one equation. I do this all the time. By the way, here's a tip for you guys. If you're going to do a whole lot of wild math work, there's two things that'll save you. One is a whiteboard in your office or your home. They're not expensive. Something you can erase and modify. Because scribbling out stuff on your paper is no good. I guess some of these newer tablets and stuff allow that fairly easily, but I like a big board to do it. The second thing is Mathematica. Mathematica will solve the most heinous equations if you want the derivative of it, the integral of it. Has anybody here used Mathematica? Well, believe me, you're going to love it, especially if you get into something where you're doing deep space physics or anything with a whole lot of variables and a whole lot of bizarre equations that you need to get a closed form solution for. Mathematica is a godsend, and I speak from experience because I spend hours and hours grueling through solutions to these things. You do it that fast in Mathematica. Back to this. I want to solve for gamma, right? So how would you solve for it? Well, you got to get gamma on one side, correct? How about we multiply everything by 82 for starters? Right? Y'all with me there? Now, next thing I'm going to do, I'm going to subtract 1 from this side. You all see what I'm up to, right? Subtract 1. So it goes away. Now I'm gonna take this to the other side. With me? It's not much trouble. So the only thing I do is take plus a to 2 over a to 1 times gamma here, and I erase it here. Now I've got that, right? Remember, I want gamma. So what I'm gonna do here is multiply everything by a to 1, which should bother some of you. It's like, why did you divide by? It makes it easier for me. So now I multiply everything by a to 1. Well, actually, let me do it this way. I'm gonna take, a to 1 here. A to 1 gets rid of that, and I get minus a to 1, right? And then I factor out a to there, and I divide by the coefficient. So what I'm left with is gamma is equal to a to 2 minus a to 1 over a to 2 plus a to 1. That's the reflection coefficient for a normally incident wave on two planar surfaces for a propagating wave. Their surfaces are planar, and it's normally incident. By the way, this is a very useful equation. And I want to tell you one thing. It's almost identical to something that you had in your transmission line portion of the earlier course. You all had transmission lines, right? Do you remember that? Do you remember when you had a transmission line with characteristic impedance Z1 or Z0 going into either a load or another transmission line with characteristic impedance Z2? The actual reflection coefficient at that boundary was equal to the impedance you're going in, Z2, minus the impedance, characteristic impedance you came from, Z1, over the sum of the two. How many remember that? Right? It's the same thing here. It's the impedance you're going into minus the impedance you came from divided by the sum. Now let's talk about practically the magnitude of either of these. Well, what if you're going into a region and it's the same thing you came from? What if a to 1 equals a to 2? Intuitively, you expect no reflection, right? Does that bear out? Well, if a to 2 equals a to 1, it's 0, isn't it? No reflection. The electric field reflected is 0. Because this is the ratio, right, of reflected to incident. What's the worst case? Well, the most reflection would happen when? Well, when one of these is overwhelmingly larger than the other. Let me show you. What happens if a to 2 is 1,000,000 times a to 1? All right. Now I got 1,000,000 times a to 1 minus a to 1 is about 1,000,000, right? Divided by 1,000,000 times a to 1 plus a to 1, which is about 1,000,000 a to 1, it would be plus 1. Do y'all follow me? All right, what about when a to 1 is much, much greater than a to 2? Well, then you would get what?
Negative.
Right, you all see this? Those are the extremes in the value. The reflection coefficient can be 1 or minus 1 is the extreme. All right, as far as the polarity, the magnitude can be 1. Now, somebody's going to come up with an exotic material and show me wrong on that. Don't worry, this is true. You know what exotic materials are? Have you heard about index of refraction? Well, there's double negative materials and things like that that we'll speak on later, but these are things that do really odd things like cause cloaking to happen. You know what cloaking is? I guess I'm out of time, but not quite out of time. I'm going to say one thing. Now, if you don't mind, I know some of you can't stay here. I would like to do an office hour now while I'm here and got you all. If you want to stay, you don't have to. How many have classes right now? And you got them in this building or where?
Yeah, it's the capstone one. Like,
How many have, what's your class?
I got RF.
All right, well, I don't want you, what I'm going to do here is just take problems. I wanted to do a problem related to this. You'll see it on video, thankfully, all right? You'll be able to look at that. If you want to stay, stay. If you don't want to stay, don't stay. I can do it on Zoom. I got you all here, and personally, this is speaking from my own experience, I much rather talk to a live class and have interactions than I do a Zoom class and trying to do things on my overhead and stuff. This is me personally. Now, I would like to do a problem related to this. If you need to go, please go. I don't want to hold you, but this is an office hour from here on. But I want to do one problem. If you don't have other questions about the lecture or I didn't put this down. This is the last thing. I'm going to just do this for completion. That's reflection coefficient. You can prove that the transmission coefficient would be E naught transmitted over E naught incident. And that's simply equal to 1 plus the reflection coefficient. This is a nice thing to know. So if you want how much field is transmitted, you got the incident field, you just multiply by the transmission coefficient. It's equal to 1 plus the reflection. And this is also equal to 2 eta 2 over eta 1 plus eta 2. That's transmission coefficient. Thank you again for doing this. I guess this won't be recorded.
Jack's gonna
I'm gonna try and figure out, video it, and then I'll send it to him.
Man,